Dr. Thomas, would you like to turn on your video, please?
Okay. That's working. I turned the camera.
Okay. All right. Good morning, everybody, and happy Friday. A warm welcome to our Friday Bayesian KOL lecture series. I'm Matangi from University of Maryland, and I will be moderating the session today. It's my great pleasure to welcome our speaker, Dr. Neal Thomas. Dr. Thomas received his PhD in statistics from the University of Chicago. He's the leader of the Statistical Research and Innovation Center at Pfizer, working on clinical and non-clinical application in several therapeutic areas. Previous work experience includes sample surveys, educational statistics, and health policy applications. His statistical research interests include design of observational studies, dose response, missing data methods, matrix sampling, psychometric models, and Bayesian statistics. So today his presentation is on using metadata to guide statistical methodology for clinical dose response. Before I hand it over to Dr. Thomas, our general housekeeping request, please be on mute during the presentation, and we will have a Q&A session at the end of the presentation. You can use the chat or raise your hand, and I'll be moderating this Q&A session. Thank you. Enjoy the presentation, everybody. And Dr. Thomas, it's all yours now. Please go ahead.
Okay. Well, I hope you can see the screen now.
Yes.
Thanks to Martin and to Frida for inviting me today. You can see it on the screen here. I've listed several of the people who've worked on this project. There have been many methods proposed and developed for analyzing clinical dose response. Most of these methods are optimal for some metric and set of conditions. Indeed, that's how many of them are derived. So one of the main things we're going to talk about today, though, is what are the relevant conditions? So what do we actually observe in practice? Now, to answer that question, we extracted data from approximately 200 compounds, dose response studies. And we try to be comprehensive. You get all the dose response studies for those compounds. That's about 400 studies, 200 compounds. That's from where I work at Pfizer and from other sponsors. So about a quarter of them are from Pfizer. The rest were obtained from other sponsors through public sources. Now, there are many therapeutic areas included here. The main exclusions were oncology and vaccines. Oncology in particular, there's different objectives, different designs and methods. So what we're going to be talking about today doesn't really directly apply there. We will cover both small molecules and biologics. And for dosing, we're going to be using total daily dose for small molecules, total weekly dose for biologics to measure dose. And there were very few adjustments required for that because of differing regimens. I'll come back to why that simple characterization of dose worked pretty well for us. Now, there could be continuous and binary endpoints. You may be wondering, for example, well, weren't there ordinal endpoints? And the answer is yes, there are a lot of them. But we were following the conventions of the sponsors of the trials as much as we could. And what we found was they always treated ordinal data as either continuous or they dichotomized it and made it binary. So we didn't have a single example of an ordinal variable. Now, the focus here is going to be on efficacy. Obviously, safety is being overlaid on this, but we're looking only at efficacy. And we're going to be looking at a single sponsor-specified landmark time point, which is usually at a point in time where the efficacy has reached a steady state. Now, all the data and all the results, software to produce those are available publicly in an R package called ClinDR on CRAN. So you can reproduce anything I'll be showing you here today. So go straight to an example. So I work for Pfizer, so I'll have to show you what, well, at least before the pandemic was certainly our best known drug is a PD-5 inhibitor for erectile dysfunction. So what you're seeing on the left, the vertical axis is change from baseline in a continuous measure of erectile dysfunction. The horizontal axis is dose. There are actually 5 panels here, one for each of the dose finding studies that was done here. So it's the same horizontal axis, even if you have different doses in different studies. Now, what you're looking at, the asterisks, red asterisks, are just the sample means. The curve you're looking at is actually a Bayesian Emax model fit. We'll talk later about how that was done. It's a Bayesian Emax model fit, and the Emax function here, the slope or the hill or power parameter, whatever you want to call it, is very close to 1. And so keep that in mind. I picked this example in part because I think this is a real prototype example of what dose response is likely to look like in your next study. That's certainly what clinical pharmacologists will tell you, and I think they're basically right, at least a very high portion of the time. The only other comment I'll add about this, the one thing that's a little bit unusual about this example is the fact that there were 5 studies. It's not exceptional, as we'll see in a moment, but it's not the norm. There were 5 studies here because those findings continued into phase 3. So these are phase 2 and phase 3 studies. Okay, so I want to start to put this into a bit of context. I want to describe what we saw in terms of study designs. So the first is, if you look at how many doses were actually studied for each compound, well, there were 39 compounds for which there were only 3 doses, and that includes placebo, so only 2 active doses. That's a real stretch to call that a dose response study, but for 39 of the compounds, that's all that we could find that existed, and these were studies that the sponsors actually called dose response studies. Now, you can see the most common dose response design had 3 active doses and placebo, but there were a fair number of studies where there were quite a few doses studied that characterized dose pretty well. Now, in terms of studies, you can see there were 144 of the compounds. There was 1 dose ranging study and 54 with 2 studies, but there were a few, 18 that added 3 or more. So the example I just showed you is a little uncommon, but not that exceptional. Now, more probably important than, but certainly related to the number of doses studied, is the dosing range study. And we're going to define the dosing range by taking the highest dose studied and dividing it by the lowest dose study. And if you do that and you look across all the different, the 200 studies, 200 compounds roughly that we evaluated, the 25th, the 50th, and the 70th percentiles, 75th percentiles for that dosing range were 3, 6, and 15. Now, 3 is really inadequate. In fact, you really can't say much of anything about dose response. And that's a quarter of the compounds. 6, still not very good, but you start to see some trends developing. 15 is still really not adequate, honestly, but you're really at that stage, you really can start to see the dose response appearing. So there were a fair number of compounds where we have really good description of dose response. We also have some compounds where we really didn't learn much. Now, another way of characterizing this is the dose spacing ratio. And what we're doing for that is taking the all the doses that were studied, ordering them from lowest to smallest, and then just taking each dose and then dividing the dose above it by that. And that would be the spacing between them. Now, not surprisingly, if you've worked on dose finding studies, 2 or 3 fold spacing is pretty common. I was a little surprised that there were actually 16% of the dose spacing ratios when we looked across all compounds that were less than 1.5. So there were some that were pretty narrowly spaced, not many, but some. 77% were between 1.5 and 3.5. There were a few that are higher. Occasionally, you'll see 5 or 10 fold spacing between doses, but not very often. Now, this is coming back to that point about how we characterize dosing. Most of the compounds were evaluated with a single regimen. In fact, 168 of them with 1 regimen, 54 with 2, but there were a few that were several regimens were studied, like once a day, twice a day, for example. Now, even among those 54 with 2, a lot of those were biologics, where one of the regimens, or in some cases 2 of the regimens, had a loading dose at the beginning. Now, that was intended not ordinarily to change the final response at the terminal landmark time, but also get the effect more rapidly. So even in those cases, the regimen wasn't really expected to change things very much. That's why we were able to characterize the dose as by total daily dosing, for example, and that worked quite well. Now, most of the studies use equal sample size allocation across dose groups. And in fact, if they didn't do that, it was typically placebo that was different, and that was typically smaller, not larger. So there's really no evidence that anybody is doing any kind of optimization of sample size here. Okay, so now I want to turn and describe that model, that Emacs model I just described. I expect a lot of you are familiar with it. Some of you maybe not. So we'll describe it here. Even if you've seen it before, I think it's useful for me to describe the notation just to remind you of the model. So the Emacs model is a very simple model. I'll describe it first for continuous data. So it just says the expected response for a continuous variable y given dose, which we denoted d, was given by this function on the right, which has 4 unknown parameters: e0, emax, lambda, this which is called the slope or the power or the hill parameter. Okay, all 3 of those names get used. And then there's the ED50. Now, when dose is 0, you're left with E0, so that's just a placebo response. When dose is very large, the term on the right, that ratio goes to 1, so you're just left with Emax plus E0. So Emax is the effect of the drug, theoretically, at least at very high doses. The ED50 is just that. It's the dose where you expect to see half of that maximum effect. And I'll explain the role of the lambda with some pictures in a moment, but that's basically going to determine how rapidly you go from no effect to full effect. Now, this model is ubiquitous in pharmacology. There are good reasons for that. I'm not going to go over the reasons I think this model is really fundamental to dose response. Now, having said that, given the limitations you already saw in design and the fact that the signal to noise here tends to be relatively low, these models are not is not unique. And so I can find other classes of curves that are similar that would represent the data about as well as what we're going to see with the Emacs model. Now, we also have, of course, a lot of binary data. It's about almost not quite half, but a lot of the endpoints were binary. And for that, there's a published literature on this. It's pretty well justified in terms of thresholding models. But ordinarily, the expectation Y, of course, are replaced by a probability now, a probability of being a responder, and that's done on the logit scale. One of the questions that get asked a lot is, well, isn't that redundant? And the short answer to that's no. That is a fully specified distinct model. So here's an example of the Emacs model where lambda equals to 1. This is called the hyperbolic Emacs model. Sometimes it's just called the Emacs model. And in this case, now I said E0 equal to 0, so placebo response is 0. I said Emax to 1, so the maximal effect is 1. And I set the ED50 to 5. Now, what I just want to point out here is with lambda equal to 1, if you take the ED50 and multiply it by 9, that's 45 in our example, that's the ED90, that's 90, where you get 90% effect. That's always going to be the case. That's what that power parameter is doing. All right. Now, that's the sort of the basic model. And in fact, the claim of the pharmacologist, which I think is pretty much correct, is that this is pretty much what dose response looks like for most clinical compounds. Now, here's an example where same setup, but lambda's now 2. So this is called a sigmoid model, and you can kind of barely see it's just starting to take shape, but this does have a sigmoidal shape now. Everything else is the same, but now if you take the ED50 and you multiply it by 3, you now reach the ED90. So this is a pretty steep dose response. I mean, you're going from the ED50 to ED90 in only a 3-fold range. In fact, this may be a little bit of a surprise to statisticians, although not the pharmacologists for the most part, but this is a really steep dose response. We don't see drugs do this very much. And dose responses with even higher hill parameters even more unusual. They do exist, but they're not very many of them. If you look at exposure response rather than dose response, I think the curves tend to be a little steeper there. We're getting something like an errors and variable attenuation when we use dose in place of exposure. But so while these exist, this is pretty steep. This is not a typical dose response. Now, of course, we can raise that hill parameter up, but we can our power parameter up. We can also lower it. So we can take it below 1. So this is an example where the lambda parameter is 0.75. It's below 1. And now you can see even at the end of the plot, I haven't reached the ED90. You get a rapid increase, but then it really crawls to the asymptote. Indeed, at least from where I'm sitting, you'd be in the Atlantic Ocean before that curve reaches the asymptote at 1. It grows very, very slowly. A couple points to make here. One is that this looks a lot like a hyperbolic model over a limited range. It's not a hyperbolic model, but it's pretty nearly indistinguishable over a finite range. This does cause us some problems because we have this near lack of identification here practically. And so what we wind up having issues with is prior specifications, things like MC, they can struggle with this because of this issue. Now, having said that, I'd like to just to discard that part of the parameter space. But actually, if you have enough data and replications, you can see that there are compounds that do behave this way. So here's another famous example from Pfizer that does just that. This is a statin that reduces LDL. So the endpoint here is % change from baseline in LDL. That's the standard way that variable gets analyzed. And this is again a Bayesian Emax model fit. The hill parameter here is all the way down, probably close to somewhere between 0.5 and 0.75. Now, part of why I believe this is real, besides it's a really nice fit, is the fact that there were 4 other statins. This is a very well-developed class of drugs. There are 4 other statins that were thoroughly studied. Each one of those has a dose response curve much like that. Different ED50s, but otherwise the same curve. They all show a rapid increase in response initially, and they just very slow gain, but it does continue to get better over with very large doses. Okay, so now I've shown you 2 examples now. We actually have 200 of these examples. So this is actually the first of 24 pages of all these examples. This was actually part of the submission we sent to the FDA when we were doing qualification work. So each one of these plots is a study out of our roughly 400 studies. And now if there were more than one study, they'll be for a compound, they'll be side by side with the same scales. Now, I'm not going to take you through all 400 of these, 24 pages of these slides, 400 plots. But if you're at all interested in dose response, I would encourage you, you can get this. It's available online. If you want it, you send me an email, I'll send it to you. A new version of ClinDR shortly. This will actually be included in the vignette for it. But if you look at it, these are Bayesian Emax model fits, and I'll describe how we did those in a moment. That's the next topic. A couple of points though. The first point is that there actually were 2 compounds where the Emax model was not appropriate. We'll come to those. I'll show you those later. But aside from those 2, the Emax model actually fit the data really well. And if you go through and look at all of them, sometimes people come back and say, what about this one? What about that one? It doesn't look that great. We've evaluated fit really carefully, and we'll come back and talk about it after we talk about how we actually did the fits. If the fits were any better than they are, you would know we had sanitized the data. And we really made an effort to be honest in the data and thorough in the data collection. We tried to include everything in here. And actually, once you account for sampling variability and the fact that we have 200 compounds here, the fits really were very, very good. Okay, now what I want to turn to next is actually how we did the fitting. And in particular, where this is going to lead to is modeling of the metadata in order to actually create a prior distribution that we can use for future compounds. All right, now this is the most involved section of the talk. So to try to help give you a sense of where this is going, I kind of want to skip to the end, and then we'll come back to the beginning and go back over it. So now our goal is going to be to form empirically based prior distribution for a future compound using routinely available information. So one of the things that took us a little while to learn is, well, what information can we realistically expect the team to have when they're designing these studies and analyzing dose response, and what can't we expect them to have? And so what we found, though, is that with the metadata was very useful for supplying information about some of the parameters that are very hard to get information about. So we're going to actually divide the world into 2 pieces. The part of the world that's going to be described by the metadata, and then part of the world, the prior distributions, the parameters that the metadata are not going to be very useful for. So the 2 that we're going to use the metadata to describe are the prior distributions for the ED50 and the power parameter lambda. Those are particularly important because those enter the model non-linearly. These are hard parameters to estimate. And in general, this model is difficult to estimate. That's why it's important to have a prior distribution. And so we're going to do that with a hierarchical model fit to the metadata. That's what we're going to talk about next. Now, this division between ones that use metadata and ones that don't is not perfect. The ED50 actually is going to use the metadata, but it's also going to use a bit of compound-specific information. Now, the prior distribution for the other two parameters, the placebo response and the effect size, the maximal parameter, are going to be based only on compound-specific information. So the prior distribution placebo response is not only compound specific, it's actually study specific. I don't know, I think I failed to mention that when I showed you the original example with the 5 studies for the one compound. But wherever we had multiple studies for a compound, we found, as has often been found in the literature, that there's more variation in placebo response than you would typically expect to see from sampling variability alone. So we just routinely, when there was more than one study, we allowed every study to have its own placebo response. But the drug effect relative to placebo was very consistent across multiple studies when they existed. So like in that first plot I showed you, that was exactly the same curve in each one of those panels. The only difference was the placebo response was allowed to differ. So they shifted up or down a little bit, but otherwise it's the same curve. So we did that throughout. And so what you're going to see is that we, for the most part, use just a diffuse prior distribution for placebo response. But if you have good historical compound-specific information, you can certainly use that to better inform the placebo response. Now that's a well-researched topic. I don't think there's anything new in dose response studies regarding that. So I'm not going to talk more about how to use historical data for placebo here. Now, in terms of the drug effect size, that's compound specific, as I just mentioned, and not study specific. Now, the most common approach here, in fact, the only one I've really seen used, is to use a diffuse prior distribution for the drug effect, imposing only a bit of biological plausibility on it. Now, you may say, well, you just showed me an example where you had multiple studies, and what about if I have a proof of concept study where I think it could be pooled as well? And if you have those, what we ordinarily do is incorporate that information through the likelihood rather than through the prior distribution. Now, turning to that hierarchical model, we'll start, with just a listing of what it looks like. So again, this is for continuous data. It's exactly just the Emacs model I listed before, but now there's subscripts on everything. So what's happening now is that I is going to be just a subscript for patient, J is going to be for drug, and then if we have multiple studies within a drug, that'll be K. And so when you look down, you look at the placebo response, that depends on J and K. This way, each study gets its own placebo response. For the Emacs parameter, that's compound specific or drug specific. That's got just a J on it. The power parameter and the ED50, again, there's one of those for each drug. That's the basic the model. Now, what we mean by a hierarchical model here, I think this audience, this is pretty routine, is we're going to look at the distribution of the ED50 and the lambda as it varies across compounds. We're actually going to model that. Right? That's the part that's going to be hierarchical. What's not going to be hierarchical is the distributions for the E0, the placebo response, and the Emax, the effect size. Those are not going to be modeled hierarchically. They're going to be assigned, each one of those is going to be in the metadata and in a future compound, are going to be assigned independent, somewhat diffuse prior distributions. But we're not going to try to characterize their distributions across compounds. Okay, now actually looking, we'll start with the power parameter because it's a bit easier. We're going to now actually talk about how the variation in that power parameter, how it varies across compounds. So we know it's quite a skewed distribution. So we're going to take the log transform of it to specify the hierarchical distribution. And then somewhat arbitrarily, we want it to be heavy-tailed, but otherwise we think it's reasonably on a log scale symmetric. So we're just going to take a T distribution with 5 degrees of freedom, a heavy-tailed T distribution. Now, the things that we don't know are going to be the central tendency, the mu, subscripted by lambda, and the standard deviation, which here is not really an SD, it's a scale parameter because it's a T, not a normal. Right? Now, the prior distribution for that hierarchical parameter, the mu, the central tendency of the power parameters, at least on a log scale, is going to be normally distributed, centered at 0, based on what the pharmacologists have told us. And we're going to have a low probability that mu is greater than, or the log of 4. So the median mu, median power parameter on the original scale, we're saying anything above 4 would be very unlikely. And in fact, that's quite conservative. It's pretty diffuse prior over the relevant range. Now, the reason we know that 4 is, remember, this is not for an individual compound. This is the central tendency of all compounds. We know that it's not 4 or even or something even larger. The reason we know that is if we really had if the compounds really were typically had a power parameter of 4, with the dose spacing we have, we would never see dose response. All we would see is no response and full response. That's not reality. We know that the dose responses of the power parameters, the rate at which they're increasing, is not anywhere near that rapid. Now, for the prior distribution of that scale parameter, we used a folded Cauchy. We also use a uniform distribution based on the literature. Now, even within those two distributional choices, of course, there's still some other features you can specify. So we actually did try several different prior distributions of this form. There wasn't high sensitivity, but there was some sensitivity here. So we'll talk about how we handle that later. So we did do sensitivity to various modeling assumptions, and this being one of the key ones. Okay, now I'm going to talk about the hierarchical distribution for the ED50. And this is more involved, why I saved it for a second. Now, the issue with the ED50 is it can vary from nanograms to decigrams. I've actually worked on compounds at both of these extremes. So even if I knew the distribution of the ED50 across compounds, it wouldn't be very useful because it'd be such a wide range and several orders of magnitude. So it took us a little while to appreciate how we could get around this issue. And eventually it occurred to us that there's always an initial prediction of this ED50. Now, it may be explicit or it may be implicit. In my organization, it is almost always explicit. But you have to have that in order to do your first dose ranging study. And if somebody says to me, no, we don't really ever have a prediction of the ED50 when we start designing our first dose ranging study, I'd say, oh yeah, you do. You just don't realize you have it. And in fact, if you don't know what it is, I'll tell you how to compute it in a moment. And we're going to denote that P50, that predicted ED50. This is the prediction at the beginning of the dose ranging process when we're designing that study. We're going to denote that by the P50. Now, there are a lot of different sources for where that prediction comes from. It sometimes comes from preclinical data, PK data. It may be a mechanistic biomarker from phase 1B. There's a lot of different places it comes from. But what we have learned is that P50 explains much of the variation in the ED50 across compounds, right? Now, one of the things we've discovered, and we'll talk about this, is that actually our designs, even those narrowly spaced ones, they're pretty well calibrated in the sense that if you look at the final data after you've completed your dose ranging studies and you look at your estimated ED50, about half the time it's above the P50 and about half the time it's below the P50. So the issue, and there is an issue here, is not that we do a bad job of locating where to place the dose ranging studies. The issue is that we're just way too narrow and way too optimistic about our information. Okay, now that P50, at least where I work, it's routinely calculated by the clinical pharmacologists. And they pretty much always do that for us. Now, having done that, seen that for quite a few compounds, one of the things we observed when we looked at those predictions of the ED50, what we discovered was that you could very reliably approximate. It's surprising how consistent our behavior was. Because when we looked at it, what we'd see is, show me the original dosing design you're considering. And to do something very simple, just look at the midpoint between the two lowest non-placebo doses. That's actually a good prediction of what your P50 is going to be. It's surprising how good that is. Now, I think the reason that's happening is a behavioral issue. I think even though there's been a lot of effort to change how we do dose ranging studies, the reality still is that people are very tuned in to doing pairwise comparisons and statistical significance. Especially clinicians are still that they're fixated on that. And so one of the consequences of that is, well, they know they're doing dose ranging. So that they know they probably should have at least one compound that's kind of got a lower response in order to have some signal of a trend. But they also, they know they want to achieve statistical significance. And the idea is, well, if I don't get statistical significance, I've wasted sample size. So they really don't want more than one compound they think is not going to work. They want the compounds in the study to have good response. So they get statistical significance. Well, that's really misguided in the dose response setting, but unfortunately, that is the mentality that still dominates. And because of that, what they're thinking is, well, what do I think is going to work? They want one below that, one lower dose, and then everything else they want to be up in the range where they think they're getting good response. And I think that's why we see this behavior. So anytime that we don't have an explicit P50, we approximate it by that simple rule of just taking the midpoint between the two lowest doses. That comes up, for example, if we're evaluating an old compound where no one's around to tell us what's going on anymore, or if we're looking at a compound from a different sponsor. Now, one of the things that helps with this is that the approximation doesn't need to be too precise. That's another reason why this will still work pretty well. Okay, now with that P50, I can tell you what the hierarchical distribution for the ED50 is going to be now. Again, it's a very skewed distribution, so we're going to log it, but we're going to normalize those ED50s now by the predicted ED50. That's the known quantity. That's a characteristic of the compound. And again, we're just going to now use that T5 distribution with with its own central tendency and scale parameter. Now, another way to think about that, I think that's a very natural way to think about it. What I like about that formulation is that you can see now that the distribution for the ED50 divided by the P50 is like giving us a way of measuring precision. Because while the clinical pharmacologist can always give us a P50, what they can really never give us or seldom give us is any idea how precise it is. It's very hard for them to come up with standard error. This is a raw empiricist way of saying, how good is your initial prediction? So of course, this is also very valuable for design purposes as well. Now, another way of thinking about what this hierarchical model is, if we write it in a more traditional form, it just says the log of the ED50, well, it's going to look like a regression formulation. It's an intercept mu plus, in this case, an offset, the log P50. Now, once you see it in this format, of course, it raises immediate questions like, well, maybe we should put a slope on that log P50. And of course, experimentally, we've done that. This is our pre-specified model. If you do that, actually, that slope does turn out to be pretty close to 1. You can also think about other compound characteristics. So like one of the questions we've gotten, including from the FDA, was, well, not so much for the ED50, but more for the slope parameter was, well, I wonder if the slope parameter is different for biological compounds than for small molecules. So also we could put in an indicator for whether whether the compound's a biological or small molecule. And to date, we haven't really found any other compound characteristics that were really very predictive of the ED50 or the slope parameter. So we're still using our original pre-specified model. Now, the prior distributions for these hierarchical parameters for the ED50, they're formed very similar to what we did for the slope parameter. So I won't go back over those here. I'll just skip forward now, talk about how we're going to use this. So now we've got this full hierarchical model. We've got a hierarchical model for the ED50 and the hill parameter, the slope parameter. And then we're going to have fairly diffuse priors for all the other parameters in the metadata hierarchical model, as well as for a future compound. So all I've done originally is to note that, well, if I want to predict the ED50, I have a new compound now. It's not my metadata. I've got a new compound I want to work with, and I want to be able to predict the ED50 and the lambda from the metadata, right, using our hierarchical model. Well, if we knew the hierarchical parameters, the mu's and the sigmas, that'd be very simple, right? It's just it's just a t distribution for the log lambda, and then once you give me the P50, I can predict, again, it's just a t distribution for the ED50 again after that adjustment, that known adjustment, right? Now, of course, those hierarchical parameters, the mu's and the sigmas are not known, but that's the whole point of the metadata. So using the MCMC and the hierarchical model fitting, we actually do now have 10,000 pretty good quality draws from the posterior distribution for those parameters, right? So now if we want to get the posterior predictive distribution from using the metadata to predict what the lambda and ED50 is going to be for your next study, all I have to do is I can draw from that distribution very simply. I take each of my drawn values of the mu's and lambdas, the hierarchical parameters. For each set of those, now I just draw from t distribution. So it's very easy to simulate from the posterior predictive distribution for a new compound. Right? Now, we can take that even a little bit step further. This is something that's been part of the literature now within the Bayesian community for a while. I've got a reference listed here. This is some work I feel was done mostly at Novartis with some academics. They described this process as the meta-analytic or MAP prior distribution. And what they noted was that if you have a posterior predictive distribution, like we have now, and you want to apply that to a new compound. So what you really want to do is to take all the metadata, combine it with the data from the new study, and get a posterior distribution for the new data to the new study once you've completed it, that takes account of all the historical data as well. Now that would be a bear if you had to go back and do that every time you wanted to get a new posterior distribution, because you'd have to go back and pull out all the historical data. Well, what they show was it's just a classic Bayesian updating. If you create that posterior predictive distribution once, then when you want to create a posterior distribution for a future compound, all you need is your prior distribution becomes the posterior predictive distribution. So you don't have to go back to the original data. You can just use that posterior predictive distribution. All right. Now, the reference suggested using a mixture of normal distributions to approximate that meta-analytic prior. Now, remember, what we've got is 10,000 draws from that posterior predictive distribution. So we want to turn that into some type of analytic form. They suggested a mixture of normals. We actually went beyond that and started looking at even ways to simplify that. And what we found was that we're taking a T5 distribution, and then we're averaging over the distribution of the hyperparameters. That's certainly not going to be a T5, but it turns out that it actually is pretty well approximated by a T5. It's not the same T5. It's a little wider, more diffuse T5. It's got a scale parameter that's a little wider. That's because you've got uncertainty coming in from the variation in those hyperparameters. But nonetheless, we found that we could actually approximate the posterior predictive distribution very nicely by a T5 distribution. Now, in terms of what we did with the sensitivity analysis, is we took that approximating T5 distribution, and then we looked across all the different, we created several posterior predictive distributions, one from each of our sensitivity analysis. They weren't dramatically different, but there was some variation in them. So what we did was we took each one of those, and we took our posterior predictive distribution for one of the more diffuse ones, and then we spread it out a bit more to make sure that we had support across all the different sensitivity analyses. They all had roughly the same central tendency, but some of them had a little more weight on the low end, some had a little more weight on the high end. We spread out the final posterior predictive distribution, our prediction of it, to be wide enough to make sure we had good coverage across all the different posterior predictive distributions that we evaluated. Now that seems like it's a pretty involved process, but actually in the end, it's really very simple for a user. All the clinical team has to do is specify the P50, and then we give them the prior distribution for the two most difficult parameters in the model. So it's really very easily implemented. All right, so to give you a sense of just numerically what these posterior predictive distribution for your next compound is going to be, and what it comes back, it says is if you want to know an 80% predictive interval for lambda in your next compound, well, the median was on a log scale back transfer. The median is going to be about 1, and it's going to an 80% interval is going to go from about 1/2 to 2. Now, for the ED50, a rough 80% interval for a future ED50, here you take your P50, you divide it by 10, and you multiply by 10, right? And that's going to be an approximate 80% interval. And that's why now you stop and you think about those original designs and you realize just how inadequate many of them are. I mean, we have a great deal of uncertainty about that P50 going, about the ED50 going into that first dose ranging study. Most of the time you're right within a 4-fold range, but it's not uncommon to be off 10. I've worked on a compound where we were wrong by 100-fold. All right, now finishing this up, let's just say we'll come back to the two parameters that were not part of the hierarchical modeling. So if we look at the placebo response, the placebo data in future trials, I didn't mention it, but almost every trial had placebo data in it, which is good. The few that didn't were really weird studies, had weird results. Now, because of that, the E0 is pretty well determined by the data we're gonna get in a new trial on dose response for a new study. So this is typically the easiest parameter to estimate. Now, of course, we may want to do an even better job at that. And if you think you've got really good TA recent historical data to use for that purpose, then you may want to add to that information. But in either case, these sources of information are just vastly better than anything we could hope to get from the metadata. In fact, it's not obvious the metadata really contributes anything about placebo response to a future compound. That's why we're not going to use the metadata to inform about the E0, the placebo response in a future study. The good news is we don't really need to. This is the easier part of the modeling. Now the Emax, or the effect size parameter, is somewhat similar, but it's really a little different situation. And the first thing to point out is just a very practical consideration, which is if you ever actually have an informative prior distribution for the effect size, even if it's pretty well justified, it's going to be really difficult to defend. You're going to have trouble getting people to accept it. So I've never been very motivated to try to get an informative prior for it, because I don't think it's going to be very useful, because it's not going to get accepted anyway. The reason for not using the metadata here to try to inform effect size is that, and I didn't say this explicitly, but you may have noticed this by now, is that the compounds in the metadata have proven efficacy. Now, there's a couple of good reasons that I won't go over those now, but one of the consequences of that is even if we had a really good distribution for the effect size across the compounds in the metadata, that still wouldn't be a good prior distribution for a future compound, which is going to be unproven, or at least far less proven than the compounds in the metadata. So it would be, the metadata would be much too optimistic for a new compound. Now, in practice, as I mentioned earlier, informative prior distributions for Emacs are just really rare. I've never actually seen us do this. Okay, so now that's a brief overview of how we actually did the meta-analysis, how we analyze the meta-analysis data, and how we're going to use that metadata to form a prior distribution for a future compound analyzer. Now I want to come back and talk a bit about checking model fit and what we've learned when we actually did look at model fit. So aside from graphical displays, the most common tool that we've used, being in the Bayesian context, is a posterior predictive checks. And the one I'm going to focus on is one that's tuned towards finding non-monotonicity. So the basic idea is that assuming the Emacs model is correct, so now we've actually got data for a new compound, or one of the compounds in the metadata for that matter, where we fit that Emacs model. We're now going to assume it's correct, and what we're going to do is we're going to compute the probability that if we ran another study, a future hypothetical study, with the same design as the study we're evaluating, and we looked at the difference between the sample mean for the best of the lower doses versus the highest dose. We want to look at what's the chance that what we would get in a future study would be as good or better than what we actually observed in our data. Now, of course, if the Emacs model is correct, it's a monotone model. We wouldn't expect the lower doses to be better than the higher dose. Now, with chance variability, especially if you're near the plateau with multiple doses, it's not that surprising to see one of the lower doses doing better, but you certainly wouldn't expect to do a lot better. So a small predictive fit probability here implies that it's very unlikely that the data came from an Emacs curve. So these predictive fits are not really p-values, but they kind of act like a p-value. So a small value is like indicative of I don't believe the model. Now it turns out we do have two compounds in the metadata where we pretty confident we got confirmed monotone response. I'm going to show you those two next. But before I show that, I want to comment a bit on the operating characteristics of these posterior predictive checks. We did a lot of simulation work to understand this. And what we found was if we just took the naive usual common cutoff of 0.05, so anything below 0.05, we'll say, oh, that's a bad fit. Anything above that, that's okay. If we take that naive cutoff as a scanning device, and we look for at how much power would we have if we actually had non-monotonicity. For example, if we were to lose half the effect at the highest dose versus the best of the lower doses, that would be an appreciable loss of efficiency. It would certainly impact the fit of the model and the appropriateness of the model if we were to see that occurring. And it turns out we have limited power to do that. Not too surprising, given how noisy the data tends to be. And so when we apply these simulation studies, we can apply it both to our analysis of metadata, so that the aggregate assessment, as well as the new compound. When we applied it to these simulations where we actually simulate the entire metadata set repeatedly and repeated the entire hierarchical modeling process, what we found is that we could rule out monotonicity at no more than 10% of the compounds. Now, I think actually, remember, we've seen 2 out of about 200. And I do think the real rate of non-monotonicity is closer to 1% than 10%. But given the variability in the data, we can only rule out something as high as about 10% of the data having, 10% of the compounds having non-monotone dose response. Now, if we accept that even that high rate, which I really do think is higher than reality, that's the best we can do with the data we have. If we accept 10% for the moment as the rate of non-monotonicity, and now we look at a collection of future compounds we're going to look at, and we ask, well, what happened if we use that simple rule of 0.05? Well, about half the time, the compounds we'd flag out would turn out to be false positives. So really fine. We just flagged them because of noise. On the other hand, about half of the non-monotone curves that we'd encounter, we would miss. So that's not a great operating characteristics. This is just really challenging. It's not surprising because the data is so noisy. Now we try to improve on that, of course. Well, in terms of false negatives, we're not going to use a rigid cutoff at 0.05. Certainly anything below 0.1 is going to draw attention. Indeed, anything below 0.2 is probably going to draw attention. So we're going to expand the number of compounds we're going to evaluate for non-monotonicity well beyond what we've described here. But on the other hand, that's going to create a lot of false positives. And we know that. And false positives, I think, are just as important as false negatives here. So to avoid false positives, we need to bring in external information. And that's crucial to deciding how you're going to proceed in any case. So what we're really going to do to try to reduce false positives is require other information, real scientific explanation of why the data did not follow the usual model. Ideally, that's going to be pre-specified explanation before we've ever even collected the data. And we're going to have a plan in place to collect correct data, the appropriate data, to evaluate whether or not we think non-monotonicity is actually plausible here. So that you'll see that in the 2 examples I'll turn to next. So this is the first example. This is in the metadata. This is where we had non-monotone dose response. It's been confirmed. This is a small molecule. I think there's actually somebody on the call today who worked on this compound. Will remember it. I remember assisting him a bit on it. And it was intended to raise HDL. So there's a percent change from baseline HDL. What's sort of the standard analysis here. Now we had a very limited design here, not too surprising, 3 doses, 6-fold range. So you're not going to get a lot out of modeling here, but we had planned to do a Bayesian Emax modeling of this. And you can see the goodness of fit, the posterior predictive check is 0.04. This really stands out. This is the worst one we've ever seen. But about a month, a little more than a month before this study read out, we actually found a publication that had just come out. I've listed it here. That actually it was for a different compound, but the same pharmacology, same endpoint. They should have done a little better dosing designs than we had done. Both of their studies showed very pronounced non-monotone dose response. So in fact, we switched the analysis plan very quickly to just be pairwise comparison. But after the fact, we still fit the Bayesian Emax model, and you can see the results here. So as you can see, wow, now we have 3 replications of this. So I'm pretty sure this is real. The biologists, there was speculation in that publication as well as amongst our biologists about why this was happening. I don't think anybody was really convinced they knew. But as soon as we saw this was a very easy decision. We just terminated the compound. There was no interest in pursuing this. That's part of why we never really understood why it happened. Now, there was a second one that was a little more challenging, a little more interesting. This is a biological to treat UC. The clinical endpoint here is a responder variable. It's a classic definition of remission. So that's what's on the vertical axis. Again, this was a Bayesian Emax model fit. It's done on the logit scale. What you're seeing is it's back transformed to the proportion scale. And this is a little better dosing design. It was 4 doses, a 30-fold dosing range. Now the posterior predictive check, the goodness of fit was 0.038. So obviously this is, and just looking at it, this one's gonna be evaluated. Now in this one, even before at the very early design stage for this compound, the lead biologist was very concerned about this compound. We knew the pharmacology, the biomarker they were trying to hit, which was anti-inflammatory, that they wanted to increase. And the drug in preclinical models and in phase 1B did just that. Nice Emax model for the biomarker. That was good. But what they had also found was that there was a pro-inflammatory biomarker that it was also influencing. It was also increasing that, which was really concerning. That's exactly what you don't want to do. Now that one also, that biomarker also had an Emax, nice Emax shape. It had a higher ED50. So the concern was that at low doses, the drug may work well, but at high doses, it might actually become harmful. So now you can see the results of the trial. It was interesting that the biomarkers are actually quite non-standard. So it took about a month after the clinical data read out before we ever got them. But when we got them, in fact, exactly what they had feared was the case. Right where the pro-inflammatory biomarker started to increase rapidly is right where the clinical response started declining. So we're pretty sure we have real biology here that we're looking at. This is a real non-monotone dose response. It's worth noting that at this stage, no one was interested in coming back and fitting some kind of flexible regression model here. What you needed was an understanding of why this was happening. We weren't interested in characterizing exactly how that response was occurring at that point. Again, we decided not to pursue developing the drug at this point. Okay, so now I've shown you 2 examples where the model didn't fit well. I want to end with an example where it does fit very well, and then talk about how we use the model to actually guide dose selection. So this is a compound to treat rheumatoid arthritis. The primary endpoint, this is may not be true anymore, but at the time was a binary endpoint. It's the ACR20. Now, very briefly, we used diffuse prior distributions for placebo response and Emax here. And the default, we also used the default priors from the metadata for the ED50 and the log of lambda. I'll mention the P50 in a moment where that came from. Now, we just did the standard fitting. Everything you're going to see on the next couple slides came right out of the ClinDR package. It's very easy to implement. We wound up with 2 dose response studies. I'll show them in a moment. We did that because the first study did not test low enough doses. Very, very common. And again, the first study had doses at 10, 30, and 60, 3 doses, 6-fold range. That should sound very familiar at this point. Now, the reason we were off a bit was because that P50 in this case was based mostly on the phase 1B, which had been conducted in psoriasis patients, where you get really rapid feedback. So the psoriasis measurements are actually acting like a biomarker for the RA. Now it turned out we actually later went back and did a full dose ranging study for psoriasis also. And in both the 1B study and in the much larger psoriasis study, what we found was that the ED50 for psoriasis was a little higher. You need a little more drug there. So it wasn't bad. This is actually, the P50 was pretty good. It was only off by about a multiple of 2, but it did cause us to center design a little high. The real problem though wasn't that. The real problem was the design was just too narrow. And we had a reasonable dosing range, we would not have had to run a second study. Okay, so now here's the data when we got it. You can see very nice fit. Again, the model was fit. This is binary endpoint, fit on a logit scale. You're seeing the back transform version of it. And we did have a trend test based on MCP mod, obviously extremely significant in either study. That's really not an issue here. Statistical significance is really not very informative at all in this setting. So what I want to talk about now, I'm not going to go over any of the details of the fit or anything. I'm just going to show you, we ran this, from this we got, a large number of high quality draws, the posterior distribution of the model parameters in the Emacs model. What I want to now just finish with is an example of how we then use that output. It's how flexible it is to really create a decision criteria that are tuned to your to the example. So basically what we did was we used the model to predict the response of the drug across the range of relevant doses. So you can see we evaluated, we predicted how the doses from 2 mg up to 30 mg would behave. Now, I'm going to focus on the left-hand side of the table initially. And what you can see is what it says mean diff. That's the posterior mean for the difference in response rate between drug and placebo. So for 2 mg, we had our posterior mean, our best prediction was a 12% improvement versus placebo. If we were to go as high as 30 mg, we would predict a 46 percentage point difference with placebo. Right now, if we look at the probability that posterior probability that the difference will exceed 20% or 30%, those are in the next 2 columns. Now, the reason for picking 20 and 30 is the commercial people evaluators told us, for this to be successful, you really want to be 30 percentage points better than placebo. That's a little bit arbitrary. It doesn't necessarily have to be exactly 30%, but they really wanted to be 30%. What they could tell us definitively was if at the end of the day, the results are below 20%, even statistically significant, we've wasted a lot of time and money. So we really wanted to be sure we were above 20. We really wanted to be at 30, if not a little bit better. So looking at that, I don't know if you can see my pointer, but for the 10 mg dose, well, we have a prediction, our best estimate, so we'll be 35 percentage points better than placebo. We're definitely going to be 20%. And we have a really good shot, not guaranteed, but we're likely to be above 30, to be at or above 30%. Now, the issue here, though, is that these are all population rates, and we're not going to observe the population response rate. We're going to get the results from a phase 3 trial. So now at this point, we have pretty good idea what the design of the phase 3 trial is going to be, a pretty rough idea what sample size is going to be. And importantly, we also know what the dropout rate is going to be. It's going to be something in the order of 15 to 20%. At that time, and it'd be a little different now, the standard analysis with the dropouts and for missing data was to impute non-response. So what you're seeing on the right side of the table is a posterior predictive distribution for not the population values, but for the observed phase 3 estimated difference between each dose and placebo. Now, if you look at that and you go across the table, you can see for the posterior mean for the observed difference, that's been attenuated, and that's because of the missing data, the dropouts. So instead of being at 35%, now it's right at 30%. We're still very likely to be above 20%. Yeah, we've got a real shot that this drug is, not surprisingly, it's right at 50% that we'll be where we want to be. But if our phase 2 data is even a little bit optimistic, we're going to be a little light on efficacy. So to be confident we have the profile we want, we would actually have to go up to all the way to 20 mg. Now you can see at 20 mg, okay, well, our expected response difference is about 36%, which is a little better, not much. Clinically, that's the 36 versus 30 is not really very worthwhile, but for achieving our objective, it actually is quite worthwhile. You say, well, we're not going to be below 0.2 if we do that. And we're very likely to observe rates in the range that we want to see if we were to go to 20 mg. Now, of course, the issue is that 20 mg, these drugs by way they're constructed, they suppress immune response. So there's a lot of safety concerns with them. So what 20 mgs is very likely to be the dose we'd want for efficacy. 10 may be good enough, but we're not highly confident. So what we did in the end was to choose 10 mgs and 20 mgs for phase 3. We took 2 doses into phase 3. One obviously very confident about efficacy, one we're much more confident about safety. But this has been done for a while now, so I can tell you we ran 4 phase 3 studies, and these predictions did turn out to be very good. As we expected, we were right around 30%, sometimes a little better, sometimes a little worse with the 10 mg dose. The 20 mg dose was, in fact, consistently better than the 30 mg. In fact, in all 4 studies, it was nominally significant versus the 10 mg dose, but that was not part of our testing plan, but by a small amount as we had predicted. So in fact, in the end, the 10 mg dose was approved, but not the 20 mg dose, and that was based on safety considerations. So in conclusion, the metadata provide an empirical basis for a dose response model for most compounds. And of course, that's combined with 100 years of clinical pharmacology research. They've known this for a long time. We're just confirming what they already knew. Now, model checking's always performed, but the model shouldn't be changed unless you've got substantial evidence to change it. It's not just the case that this model predicts dose response pretty well. It's what dose response should be. And if it's not, that really does, it's a good indicator that what's going on here is not good. You're probably not going to be happy with this compound in the long run if that happens. So the second thing, though, is that which we didn't appreciate when we started this, we were really just looking at that first bullet point originally. But what we came to appreciate is that the metadata could also supply an empirical basis for a Bayesian prior distribution. And given how difficult these models are to estimate, that's really important. Now, I didn't discuss it today, but the Bayesian model also has good operating characteristics. And I just want to end with one final point, which is that since we finished that metadata collection, we now have, at least by the end of this year, about 5 additional years of data that are potentially available that'll be complete. That's roughly, we expect, in the order of 50 to 100 additional compounds if we do it exactly as we've done it in the past. So there's going to be a real opportunity very soon now to expand the data collection. And of course, at that point, everything's going to change a little bit. To the prior, everything will change at that point anyway. So it's also a great time to update and change the methodology. Those changes could be just small tweaks. It could be a complete rewrite of how we do this. And one of the things I would like to see done is maybe also try to expand this to include longitudinal data. That would put us in much better alignment, statistics with clinical pharmacology and with pharmacometrics. I think both groups would benefit from that. So I hope I've interested at least one person on this call to be interested in really stepping up and taking ownership of this. I'm happy to get you started, but I'm too old to complete this at this point. So I'm really hoping that somebody will be interested enough to pick this up and move on. Okay, Frida and Martin G, I'm done at this point. I don't know what I need to do to pass control back. Should I stop sharing the screen?
Yeah, thank you, Dr. Thomas. You can leave it as it is,
okay.
and we can
great.
open the floor for questions. Yeah. So anybody, first of all, thank you for a great presentation. And anybody having questions, please feel free to use the chat or
hello.
Yes.
Hello, can you hear me?
Yes, Dr. Tiwari. Yes.
Hi. So this was a great presentation, and particularly I learned a lot about Emacs model, and we have been exploring Emacs model at BMS. And we are trying to validate and see similar kind of results if we can get. Our FarmClean people have also validated and are looking into this. My question is a very basic question and maybe naive, so I just want to be upfront with that. I just wanted to understand that I know that the priors are built using the metadata. What happens if I don't want to use the metadata and I naively proceed with a non-informative prior? How far I will be off from what you are getting?
Okay. Yeah, so, well, the first answer to that is, well, it's very much going to depend on the data in your study. If you have really good data in your study, you know, a really nice dosing design and it's well targeted, you have a high signal to noise, probably not that different. On the other hand, that unfortunately is the exception to the rule. There's a very good chance, well, if you do maximum likelihood, which is sort of another way of doing that non-informative analysis you just mentioned, I'd say your chances that you're going to get convergence within the parameter space, you know, is no better than 50%. MLEs just fall over here routinely. I mean, you can get lucky, you might, but there's a very good chance you're not. Because again, if you go back and you start looking at those slides from even that one out of those 24 pages, it's not uncommon that all the doses are low and you're on the linear part of the dose response curve. You're not going to be able to estimate the Emax or the ED50 parameter. Right. On the other hand, equally often, all the doses are on the plateau or very close to it. You're not going to be able to estimate the ED50 or the slope parameter in that case. So it's very common that the model is not very well determined. In fact, one of the struggles we have internally is that what we see is that there's not, if you're estimating a dose response curve, and the ways we're using is, it's actually the response function that we're really interested in. That's not terribly sensitive to that prior or to our prior. I mean, it can be sensitive if you go completely uninformative. That really, for me, is a non-starter unless you've got great data, which you don't want to count on that. But what you find is that the fitted curve and the inference about it is not too sensitive to the prior, at least if you have a reasonable prior. But what is very sensitive to that is the individual model parameters. They are not very well determined. And I always take them with a grain of salt. What you report for those parameters, unless you have really good data, is pretty darned unreliable. And with clinical data, it's all, even when you have pretty good data, they're still not that well estimated. Put this in context, another place these models get used a lot is in various preclinical contexts. I just recently reviewed a paper about expanding the Emax model in a particular way in a preclinical context. They had the obligatory example and the obligatory simulation studies, and in both, they had a 10,000-fold dosing range and a signal to noise ratio of 5 and 10 in their simulations and in their example. We can only dream of that with clinical data. We're nowhere near that. So our ability to actually determine the individual parameters of that model is very poor. Even when we have what is relatively good data in a clinical context, it's still very hard to do that. So we actually discourage people from emphasizing. We report the model estimates and the standard errors and the confidence interval, the posterior intervals for that, but we really try to de-emphasize that. You shouldn't take them too seriously. So that I don't know if that's answers your question directly or not, but I think you'll find, even for the purpose of estimating the dose response curve itself, not the individual parameters, you're going to struggle if you put diffuse priors on all the parameters.
Yeah, thank you. I think it does, and really appreciate your answer. Frida, may I ask another question, if that's okay?
Yes, please go ahead, Dr. Tiwari.
Yeah.
I don't see anything on the chat. Yes.
So my other question is, Dr. Thomas, is that we looked into the prior and the posterior for some parameters, and we found that for some parameters, the support of the posterior was completely disjoint, I would say, from the support of the prior distribution. In other words, the prior and posterior were sitting completely on two different supports. And that is something, I'm not sure why it is happening, but it seems somewhat anti-Bayesian that your prior has one support and the posterior is way off and it has another support.
Yeah,
have you
I can't
that?
answer that without seeing. You'd have to send me share an example with me. That shouldn't be happening. I've never seen that happen. I suspect there's something wrong somewhere. Yeah, that's definitely. a sign that something is broken down somewhere.
Yeah, just wanted to know if you had any experience. Thank you so
No,
much.
I
I
have
really
not seen.
appreciate
I
it.
mean, we certainly see examples where something was broken and it was usually
Yeah,
a bug somewhere, but I no, that shouldn't be happening.
thank you so much again.
Yeah, anybody else who wants to go, please go ahead.
So I know that this model is mostly meant for dose selection, and so the overall dose response values are most important. But do you feel that you can draw a lot of conclusion from the parameter predictions from the Bayesian side, or are those just something that are still much less important than the actual predicted response?
Yeah, I think I started to address that with the previous question. Again, that's somewhat dependent on the data you get. I mean, if you've got a really good design, and one of the key things is obviously is not only having a good design, several doses spread over a substantial range that are well targeted, but in addition, the other thing that is going to dictate how well you can actually estimate the dose response is the magnitude of the signal. Of course, that's also related to sample size. If you get big enough sample size, you can have a small signal, but practically for the size studies we run, you need a pretty good sample size, I mean, a pretty good effect size. And in that comment, although we don't use the effect sizes from the metadata as explicitly for the prior reasons I mentioned when I was going over it, they've nonetheless informative. And what we've seen is that the effect sizes run anywhere from about a half to a little bigger than 1. There are a few exceptions. Antivirals, for example, you can get effect sizes of 4 or 5. Those are wonderful. That's one of the reasons why we make progress so fast with them. But for the most part, for most real clinical endpoints, something like LDL, which we think of as the endpoint, clinical endpoint, is really not. When I say clinical endpoints, these are things where a clinician or a patient have really assessed the condition as opposed to a lab. It's unusual to see effect sizes above about 1.5, and between 0.5 and 1 is very common. And the challenge with that, unless you've got really big sample sizes, is that you're looking, you can detect, you can differentiate from placebo, but you're really looking at very noisy data points within that. If you look at your sample means or sample proportions, they're going to vary a lot. And in fact, I think it's one of the points that causes a lot of confusion, both for clinicians and statisticians. I went to a talk one time where a statistician began their talk by saying dose response can look like anything. And I thought, in fact, it's one of the things that motivates research. I thought, I don't really think that's true, but I can understand why people get led to that conclusion, because they're looking at very noisy situations. And when you're in a situation like that, either you don't have a great dosing design, or you've got a small signal, you're really not going to nail down the parameters of that model very well at all. And in those settings, you really want to de-emphasize the interpretation of it. Yeah, you show people, but you also need to warn them that, this is going to be these parameters, their values that we're reporting here are quite dependent on what we assumed. So that's a long way of answering it, of saying you really need to look at your data. If the curve's well determined, you probably can talk about those model parameters. But if it's not really well determined, you probably want to avoid staying away from that.
All right, and that's true even with the Bayesian models. Okay.
Even with the the beauty of the Bayesian models, it won't fall over. It will, and actually, if you look at this was a big question for the FDA during when we were reviewing the submission. We showed them, because they were asking this question. Well, look, this is a terrible dosing design, and there's hardly any information here, but you've got a fit. Now, does that make any sense? And we come back and say, yes. If you look at the fit, and you look at the inference we're making from it, what you can see is that what we said about it was exactly what you could reasonably say about it. So in some cases, you could say, well, we know the dose response is not above, the effect size is not above here. We can't say how low it is. In other cases, we say, well, we know the effect size is at least this large, but we can't say how big it is, because all we saw is the linear part of the dose response curve. So what we can show them is that the inferences we're getting for the dose response curve made sense, even in settings where we had very limited information. But they were very limited in what they said, which was correct, that they should be limited there. So if you look at the data, in any case, you can say make some statements like, well, I know that the effect size is at least this large, or, well, I know that the effect size can't be any larger than that, because what I saw was the plateau, and I know that so I know it's not going to be above the plateau. So what you can say is, in any given example, is limited, but the Bayesian model actually parses that data very nicely. So it comes back and makes inference about the things you actually can infer, and it doesn't make inference about the things you can infer. And it does that without falling over. If you take that diffuse prior distribution that was mentioned earlier, or worse still, which is essentially equivalent way of doing it, just numerically different, is try to do maximum likelihood, you just can't do that. It won't come back and give you reasonable answers. Another place where that happens is routine, is if you actually have little or no response. If you try to fit maximum likelihood, more likely than not, it's going to crash, because the model's not identified when the Emax parameter is 0. The Bayesian, in this case, comes back and fits a nice flat curve right at 0. Inferentially, it does the right thing for you. But what did the parameters mean in that case? Well, absolutely nothing, right? But it still produces the right curve for you. So in that regard, the Bayesian model is a lot more robust. It can handle not so great data. And unfortunately, this is obviously one of our pushes here, is to try to get better dose response data. That's, in the long run, if we can get that to happen, this is all really worthwhile. And that's way more important than any discussion about Bayesian analysis. But in the meantime, the Bayesian approach actually does parse that data well. It handles partial data a lot better than any other approach. And it does give reasonable answers in those settings.
All right. Thank you.
Any other questions?
Yeah, I have a question. Under this model fit section, this for posterior predictive checks, this GOF boundary value of 0.05 is chosen for indicating lack of fit of the model. Dr. Thomas, can you please give some explanation about why the choice of this 0.05 value, which would indicate this?
Okay, well, yeah, the main reason for that is tradition. 0.05 is 0.05. We actually did look at a lot. I don't have the slides to show you right now, which is good because we'd be here all afternoon. But actually 0.05 is not so bad. I actually think, again, as is discussed on that slide, I've got it displayed now. I think actually you probably want to be a little more generous than that, and look at things that are a little higher. Again, with posterior predictive checks, they're not really p-values, but they do behave a lot like p-values. And actually, if you look in the publication, I can't remember which one it was. One of the publications is Statistics and Biopharmaceutical Research. It's actually also in the review documents from the FDA posted. We're going to actually put that document into the vignette in a new version of the package very soon. If you want to see it in the meantime, if you just email me, I'll send it to you. But what you can see is that, and this is true of posterior predictive checks in general, because you're not actually going to apply, we're acting as if, what's the probability for a new future study? But we're actually applying that to the existing study. So it's just like with frequentist methods, it tends to overfit a little bit. It tends to agree, the posterior predictive checks tend to be a little conservative because, we actually use the data to fit the posterior that we're then evaluating. So it tends to agree with the data a little better than it should. So if anything, the p-values that these predictive checks tend to be a little high. So in general, we would usually look at something a little higher than 0.05. So at least as a screening device to say whether or not we think this is worth evaluating further to check it. But having said that, as I discussed, the real danger here is that, especially, if you've got an ambitious clinician working on your project, anybody who's got a bit of pharmaceutical experience as a statistician has experienced this. If they look at your curve and it trims off one of the higher doses that happen to be, noisily looks good. Probably just sampling variability, but it gets them to the objective that had been stated for the drug up front, and the curve doesn't. Right? They're going to come up with 100 reasons why we should throw the curve away and go with the point estimate that they like. Right? That we know that happens. They're always doing that. And so what you really got to avoid, and for the model to have value, is you got to avoid that happening unless there's really good reason for doing it. That's why you really want to emphasize that you need substantive evidence to go along with that small p-value, that small predictive fit. So in general, the 0.05 was really just for us when we were looking at operating characteristics. That's just what we chose. But in practice, we wouldn't use 0.05. We'd use something higher to screen with. Even something at 0.2 would probably be enough to make us suspicious.
Okay. Thanks for the explanation.
Yeah. Any other questions? Yep. Please feel free to unmute yourself. Yep. I don't see any so far. Okay, yeah, I think then that brings us to the end of the session. Thank you, Dr. Thomas, for such a great presentation, very interesting topic, and thank you all for joining today. Have a great weekend. Yeah, thank you. Bye.
Thank you. Bye-bye.